Okay, it's 11:40. I guess we get started. I spare you the usual intro of how sad it is we can't be in Oslo right now. It is very sad, especially since we all can't go to the Dubliner tonight. So, so let's just do this from the same chair that I'm sitting in now for the last 12 weeks. I got older, longer hair, glasses, all that. But very exciting topic for today, right? It's about OpenID Connect and OAuth security best practices. And before we start with that, just one thing, I will upload those slides directly after my talk. I didn't have the time to do it before. That's what I normally do. I will upload them, and you see that basically it's going to speakerdeck.com/least-privilege. That's where I upload all my slides. So maybe the archives are interesting as well, but I will upload this particular slide deck right after my talk. Okay, good. Enough about me. Why are we here? So I've been actually working for the last 2 or 3 years with, for the Norwegian government, basically, to introduce OAuth and OpenID Connect into the health system. So they're getting rid of an old system, decided to go for token-based security and for OAuth and OpenID Connect and for identity server, which is nice. But as you can imagine, especially in healthcare, there are so many laws and special regulations and rules and so on that the plain OAuth, as it is in RFC6749, is not enough. You need a more secure profile of these protocols to tailor, to cater for these industries. And so we've been working on this profile. Actually, another industry which has similar needs, the banking industry, is working on a similar thing called FAPI for financial APIs, and we in the health system are working on HAPI, which is for health APIs. And it turns out that something very similar in parallel happens in the States for like government and enterprise OAuth 2 profiles. So basically, what this talk is an excerpt of training material I've been creating for the last 6 months or so, which talks about basically security best practices in OAuth and this new thing called OAuth 2.1, which we'll talk about at the end. And then the second talk, which is later today, I think at 3 o'clock, is think of it as the part 2 of this talk, where we talk about new specs that are either partially done or already released that help you improve the security of an existing OAuth deployment. So these are all the topics, and they are from this new training I just launched a couple of weeks ago, and that's way too much material. So I will pick for this talk and for the next talk just the things that I think are the ones that you must hear about. Okay. One word of caution, right? If you're going to start learning more about this, you will ultimately deal with documents that look like this, right? It's the fun stops here, right? It's a Korea font. You get this funny ASCII art, for example, things like this, right? Even clicking this PDF link will not make you happier if you don't like that format, because it looks exactly the same as the website, right? But actually, it turns out for the newer specs, they now have nicely formatted HTML versions of that. So if that is easier on your eye, totally fine. But one of the reasons why this is the way it is basically because you can read it with any browser. So if you just use the very first browser ever created, right? You can basically you're saying you're seeing only PowerPoint. Is that correct? And no console window? Oh, okay, well, then let's go back to PowerPoint. Anyways, not so important. We only need PowerPoint for the rest of the talk. But yeah, so my point is, Okay, you see the console. Well, man, you totally derailed my train of thought now. Okay, forget the console. Anyways, we go back to PowerPoints. Anyways, my point was this talk will talk about the upper half, which is about common attacks, common countermeasures, security best practices, and so on. And then the second talk will pick out some of the topics from the, when you go beyond the OAuth 2.0 and 2.1 spec. But let's give you some context first. So when we look at a timeline, how things have happened and why they happened, like we go all the way back to 2005, where basically that was the birth, if you want, of web-based authentication, right? Like the fundamental pattern that you're authenticating a user, you're sending the browser to some place, and that some place calls you back with something like tokens. That is all being, goes back to the SAML 2P protocol, and then WS Federation protocol and WS Trust for more like web service style communication. That was very enterprisey, XML and so on. And shortly after, the consumer space discovered the need for token-based protocols as well, right? I mean, fundamentally, this was the time where, you suddenly had new scenarios where a third party wants to access your Gmail account, but how do you do that without exposing your Google password to the third party? So they came up with this thing called OAuth 1.0, which is basically a protocol for requesting access tokens to access resources on behalf of a human being, typically. OAuth 1.0 became very, very popular. And a couple of years later, like all the big companies jumped on it, like Microsoft and, like all the enterprise people that before that were rather in the SAML and W star space. They now wanted to shape the future of OAuth. And that ultimately became OAuth 2.0. And one of the themes in OAuth 2.0 was like simplifying the protocol, because OAuth 1.0 had a lot of crypto going on. And they simplified it to a point where people were unhappy about the security that got lost along the way. So, for example, the thing called bearer tokens was a new thing in OAuth 2.0 that didn't exist before and is arguably less secure than the proof of possession tokens they had before. And maybe you heard about the history that the spec author left the IETF like with a big bang and made this final talk about OAuth. And if you're interested in seeing that talk and why he left, just search for the word, your favorite swear word, OAuth. Okay, you probably find it. Anyways, part of the legacy of this spec author was that he demanded that there was, the token usage should be specified separately, so that shortly after we could come up with a proof of possession style of token usage. Never happened until just recently, and we'll talk about this in the next talk. But also, the other thing was that they created a threat model for OAuth, because the problem is that OAuth 2.0 has so many variations, and you can, even if you follow the spec, do an insecure implementation of it, because it gives you so much room for interpretation or variation, I guess, yeah? So they created this threat model right from the start and made sure that this got published at the same time as the protocol itself. But the threat model, to be honest, is a bit theoretic, yeah, because it was created before we learned really how people will use OAuth in the future. And, since we didn't have the real world use cases, it was rather, as I said, a bit theoretically looking at the various threats and risks and countermeasures and so on and so forth. So in other words, it is interesting for security professionals, but not very actionable for a developer, for example, because there's no concrete guidance in there. Yeah. Anyways, lots of things have happened. Many protocols have been built on top of the OAuth 2.0 specification. It became more popular, right? And at some point, people said like, well, we also see security problems with OAuth. We need more guidance. Yeah, and the very first guidance document was published in 2017. It's called OAuth 2.0 for native applications, and it's what they call a BCP, a best current practice, right? And it's good that the word current is in there, because the older the document gets, the less current the guidance is, of course. But this is still pretty good. And it gives you concrete guidance about, like, if you're writing an Android app, do this. If you're writing an iOS app, do that. If you're writing a Windows desktop app, do that. So basically the idea was, let's give people, developers, implementers, more actionable guidance to secure their OAuth installation. So, and then more BCPs have followed. There's one which got published last year, which is called the JSON Web Token BCP, which talks about how to securely use JSON Web Tokens. And if you see that picture, that's 5 years after JSON Web Tokens got specified. Yeah, and a couple of new ones will be published this year. The most important being the Security Topics BCP, which is basically, think of it as the version 2 of the threat model, but this time much more practical. And there's one which many people have been waiting for. It's the browser-based BCP. Okay, and in the future, soonish, there will be OAuth 2.1, and we'll talk about what this is. And then in the more distant future, there is something currently codenamed OAuth 3.0, which is which will still take some time. Okay, so what this talk is about, basically give you an overview of the most relevant things of the documents you're seeing here. And as I said, you probably need more time and follow these URLs and have a better read, because as I said, I can only give you an overview in 60 minutes, and there's much more to read here. Okay, so just the big picture, right? So a token-based system pretty much looks like this, right? So you have front ends, you have back ends, and you have back ends for back ends, and you have different call patterns and different client types, and you want authentication, and you want API access, and you want single sign-on, and you want delegation of identity to back-end services, all the things, right? And the security token service is the abstract thing that is like the traffic cop in between, that issues the tokens, and that's where you implement OpenID Connect. So to simplify this a little bit, yeah, it basically always looks like this. Yeah, you have a human being, maybe, but you definitely have a client. A client is a piece of software that wants to access a resource, yeah, which for all practical purposes typically is an API. The client cannot access that resource directly. It first needs to go to the authorization server and ask for permission, if you like, and that gives them a token. And with that token, they can access the resource server. And we basically have two types of clients. One are the more like the machine-to-machine style clients, where no human being is present, and the other part would be the interactive clients, like a web application or something like this, a native app, where a human being is present and authorizes the client to access those resources on his behalf. Yeah. So if we want to look at the security properties, or rather the risks of such a system, right, we have to look at the attack model and see, like, what are the attackers that potentially, would attack this system. So I found the cheesiest, possibly cheesiest symbol for an attacker, for a hacker, right? So excuse me, but the first type of attack is basically, we say, when an attacker can read or write unprotected network traffic. Yeah, and that's an easy fix for that, right? You have to use TLS for everything. The specs are not always clear. But it's pretty much, a known thing that you have to use TLS for every single network interaction. If then an attacker can still access network traffic, well, then your TLS infrastructure is compromised, or even worse, maybe your DNS is compromised. And that is a serious problem that network people need to fix, but nothing that we as developers can do. So that's not our problem, basically. The other attack that is not strictly speaking the problem of the OAuth or OpenID Connect implementation is if an endpoint gets compromised, and with that we mean unrelated to OAuth or OpenID Connect. Yeah, maybe on the server there is I don't know, like a telnet endpoint which is unsecured, or a cross-site scripting attack or a SQL injection attack, something like this that is, not related to the OAuth endpoints, but still allows an attacker to take control over an endpoint. Yeah, again, not our concern, at least not from the point of view of this talk, right? I mean, it is definitely our concern, but not for the protocol. What definitely is a protocol concern is if an attacker can mount additional endpoints. And that, to be honest, is the most interesting part these days, because attackers find creative ways to use the system in a way that you haven't foreseen it. So what if, for example, an attacker can mount a rogue authorization server, or if they can mount a rogue client or a rogue resource server? And that gets even more exciting, I guess, if they can trick the legitimate client to use the rogue authorization server, or can trick the legitimate user to use the rogue client with the legitimate resource server. Like all of these permutations that, are probably legal protocol interactions, but executed in a way that you have not thought about it or have not protected yourself against, right? I'll show you an example later of that, which is brilliant if you think about it, but also devastating. Yeah. The good news is that by far the most attacks just happen because of plain programming mistakes. Yeah. So by far the biggest group of attacks are basically where the attacker can read but not modify the contents of the authorization request or response. Yeah, and that might be enough to compromise the system if they are clever enough, right? And that might happen because you are leaking data, because you might have open redirector attacks, because maybe you're leaking data into the browser history, into proxies, into log files, something like this, right? The good news is they can all be fixed. These are just, knowing the right keystrokes, you can fix them and can solve the problem. But still, by far, that's the biggest group of problems we've seen in the past. Okay, so these are basically the adversaries that we try to protect against. Now, these security guidance documents have been in the works for quite a while. No one was paying attention to that until, I guess, that is late 2018. One of the authors, Thorsten Lodderstedt, which is a well-respected colleague of mine, wrote this blog post. You should stop using the OAuth implicit grant. And he basically said, like, if you do it, you might, this might result in attacker accessing your health records or initiating a payment from the bank account. And to be honest, the way it was written, it was a little bit, so the next day I got emails from customers or on Twitter or, basically people thought like, oh, have you read this blog post? They found a new vulnerability in OAuth. And that is, of course, not the case. He didn't find a new vulnerability in OAuth. He just said that from all of the ways you can use OAuth, the implicit grant is the most problematic. And that was from the start known. And if you have read the threat model, it's in there. Yeah, all of the problems with the implicit grant were written down from the start. And, just to recap why this really exists was that back in 2012, they were looking for a way to give a JavaScript-based client easy access to the OAuth protocol. And remember, in 2012, it was not possible to use AJAX calls cross-domain because we didn't have cores by the time. Yeah, so they found a way, or hacked up a way, whatever you want to call it, that allows you to basically, do everything on the query string parameter. So you send the request over the query string, and then you get back the tokens over the URL back to the client. And as I said, this was a workaround because in 2012, cross-origin AJAX calls were not allowed. And we found many problems with this approach because leaking is easy here, right? It's on the query string, it ends up in the browser history, it ends up in logs, and so on. So long story short, in 2020, we totally solved the cross-origin AJAX problem. So there is no need anymore to transmit tokens over URLs, okay? It's error prone, it is hard to secure. We should not do it anymore, which doesn't mean that if you are doing it right now and you implemented all the right countermeasures, you have a problem. Yeah, all I'm saying is it is a very risky way of doing things, which is not necessary anymore. Okay, so first takeaway, don't use implicit flow anymore. If you have existing ones, think about rewriting them. I mean, which is not a rewrite of the app, but just changing the protocol flow. Okay, while we are at deprecating flows, the next one that is not recommended anymore at all is the password grant, right? The password grant is this flow in OAuth where you harvest the credentials of the user in the front end and then send them to the back end to get a token back. The main problem is that the user types in the credentials into the client application and not into the authentication server. Users should be educated to only type in their passwords in one place, which is the system that owns the account, right? And research shows that the more often you type in your password into different places, the more prone you are to phishing attacks. So avoid that as well if you can. Also, the password grant is not compatible at all with modern authentication methods like FIDO, you know, two-factor authentication, federation, and so on. Many of the popular commercial authentication systems don't even allow to use that anymore. Okay, so that's another thing you should think about. Okay, which basically is a good thing, yeah, because if you look at all of the different flows and variations we had like 1 year ago, yeah, depending on which type of application you're writing, you had like many choices, right? And many choices means you have to understand the different properties of all of these choices and their advantages and disadvantages and so on, which basically became harder and harder. Now with the new work and looking at the system with a bit of hindsight, it's actually nice that we can shrink down our options, which means that you need to know only two flows really. Which is the client credential flow, which is for non-interactive applications like server-to-server style communication. And it's the code flow with this little extension called Pixie, which I'll show you in a second, for all the others, basically wherever a human being is involved, which dramatically simplifies the learning curve and less options gives you more security. Okay, so let's have a look at machine-to-machine first. So, machine-to-machine, basically, it's pretty simple. You have the client, you have resources or APIs, and you have the authorization server. The authorization server knows about all the clients, about all the APIs. It knows about which client is allowed to access which API. So the client goes to the authorization server, authenticates with the authorization server, says, hey, give me a token for, API 1 or API 2. And if that is allowed, the authorization server returns an access token back to the client, and then the client will use that access token to contact the APIs. Now, some things we can't cover here, but I still want to mention them is access tokens have been unspecified by OAuth itself, right? So when you look up the original OAuth RFC, there is no mentioning whatsoever how an access token should look like, what's the format, what's inside, what's the semantics, and so on. It just says there is an access token, and that is what gives you access to the APIs. Yeah, there's a lot going on in that space, especially since I guess the industry as a whole decided like that JSON Web Tokens is the preferred way to do access tokens, right? So if you look at, or if you are using JSON Web Token as access tokens, you should definitely have a look at the new JSON Web Token BCP, which talks about, like what are the best practices in which crypto, algorithms you should allow, how, you know, like common vulnerabilities that we found in JSON Web Token libraries. The good news is if you're using the Microsoft JSON Web Token library, then you're good. Yeah, and this one is not vulnerable to any of the known attacks. Also, there's a new document which you should have a look. It's called the JSON. It's the JSON Web Token profile for OAuth, and this kind of like tells you or gives you a common language, if you like, how to use JSON Web Tokens in the context of OAuth. Which claims should be there? What are their names? What are their formats? What are the semantics and so on? Yeah, so that is something that you definitely should have a look at. Another thing that definitely you should revisit in 2020 is how do clients authenticate with the authorization server. And, you know, it's a very common practice to have shared secrets, right? I mean, that's just one step up from the API key that many people were using. Shared secrets are easy to get started with, right? They sound easy to use to begin with, but they are a bit of a management nightmare, right? I mean, they are shared. That's the first problem. Yeah. So how secret is a secret when it's shared? They have to be, you know, they're symmetric, so they have to be at both the client and the server side. They should have a high entropy, right? You should not store them in reversible encryption, meaning you should hash them on your authorization server just in case that if somebody is able to breach your configuration database or system, that they don't get, you know, all of your client secrets in clear text. Configuration management is a bit of a problem. They need to be transmitted over the wire, right? That's another thing. What if the network you are crossing is untrusted? Yeah. So potentially the network admin of that network, you know, like has access to your clear text secrets in proxies, things like that. So, you know, they are a bit problematic. Asymmetric keys instead solve many of those concerns, right? Because there is no secret anymore to store on the server side because it's just a public key. The secrets don't get transmitted over the network. You can attach other properties to it, like expiration of secrets or replay detection of secrets. And in the next talk this afternoon, I'm going to show you basically a way to fix that using a technique called private key JSON Web Tokens, where you basically exchange, you know, replace that symmetric key with a client generated JSON Web Token, which, you know, solves many of these problems. Yeah. The other thing we're going to talk about this afternoon is how to solve the bearer tokens problem, right? I mentioned it earlier that one of the concerns with OAuth is that the tokens are not bound to the client. Meaning, you know, if you are, you know, it's like cash, right? Money. When you lose your money on the street and somebody finds it, they can use it, right? There's no binding of the banknote to the owner of that banknote. Unlike credit card, for example, yeah, where there is a certain binding there, you know, in real world might not be as strong as we want, but still there is something like a PIN maybe, or a, you know, like a signature or a picture, something like this. Yeah. In OAuth, up until recently, we didn't have that. Yeah, all tokens were bearer, and if they leaked somehow over the wire, anybody, especially, you know, the bad guys, could use them to call the APIs impersonating the original owner. Yeah, that is, you know, one concern from calling client to server, but it might be also a concern if maybe you are leaking that token to a malicious server, right? Maybe you're calling the wrong API with that token, and now this API has that token, and then call the legitimate API instead, right? And the legitimate API doesn't know the difference. So again, that is something you should consider. Especially if there's a chance of, you know, again, leaking or, you know, tokens being used in weakly secured clients, or maybe tokens traversing untrusted networks. There, we can make this stronger. And again, I'll show you techniques for that in the next part this afternoon. Okay. Let's have a look at interactive applications. They are the far more interesting target for attackers because they are easier to attack because there are humans involved. Yeah, and these humans, not only humans but also browsers. Yeah, and browsers are as you know, browsers are very powerful. They are very useful because they can show a UI and they can follow redirects, right? The problem is that browsers can also show UIs and they can follow redirects, and it might be the wrong redirect to the wrong UI, and the user might not be able to distinguish that, right? So since the whole browser-based interactions are based on sending people back and forth, these back and forth things are very interesting targets, right? So just to summarize that, how does a browser-based flow work? Basically, you send the user agent to the authorization server. The authorization server shows the UI to log in the user, to maybe do consent and these things. And then the authorization server sends back a so-called authorization code. And then the client application opens a back channel to the authorization server, hands in the code, the client ID, and the client secret, and gets back the tokens. And from that point on, the client can then, A, authenticate the user, and B, call APIs on behalf of the user. Now, as you can imagine, these two redirects here, they are the main target, right? So let's have a look at attacks that specifically target the redirect URI, okay? So the original OAuth spec did not make any statement how you should validate these URLs going back and forth to do the redirects. Yeah, the threat model did, and also the OpenID Connect specification did. They say you should never ever have any sort of variables in there, right? Like you should do a strict exact string matching, even case sensitive. Yeah, and the reason for that is basically these callback URLs, they are very, very sensitive on that URL. You are running your very security relevant token validation code, for example. And if you, and the better you can isolate this code into a single place, the better. The moment you are allowing variables like this here, star.somesite or somesite/star, you are opening up the attack surface, basically, where tokens can be sent to, and potentially there's a bug on this URL that allows leakage, forwarding, open redirection, things like that, okay? So you should minimize your attack surface by only allowing a single callback URL, or at least a very specific set of particular callback URLs, and not give the attacker a chance to insert star. Okay, let me give you two examples of things that happened in real world with these approaches. So last year, I think it was Electronic Arts, EA, that had a subdomain takeover attack. And the way this works is basically, in short words, is let's imagine, you are creating a new application. You go to Azure, you register your Azure web app. It gives you foo at azurewebsites.net, right? And then you write your application. And at some point, somebody adds a DNS entry to that, so that this foo thing becomes part of your DNS namespace. Yeah. So EA had billing.ea.com, and that was an allowed target for a token. So it was an allowed redirect URI. Okay, all good so far. But at some point, the billing application was moved to another part. So they shut down the foo website on Azure websites, but forgot to remove the DNS entry. So now suddenly you had billing.ea.com pointing to a non-existing Azure website. And you can query the DNS server and find out that this is the case. Yeah. So what the attackers did was they registered foo at .azure websites again, because that was free, right? And suddenly billing.ea.com was pointing to an attacker website which was able to A, execute code under the EA domain, and B, was a valid redirect URI now for tokens to leak them to an attacker controlled site. Okay. That wouldn't have happened if they would have been very strict with the redirect URIs. And I guess, yeah, I mean, these things happen, but you can't have a defense in depth here by being more explicit. The other thing that happened to, for example, Facebook and also GitHub is this here, like allow site/star. For example, Facebook allowed for a long time the redirect URI to be any page on Facebook, and I think GitHub had exactly the same problem. Yeah. So if that's the case, what attackers would do basically is they will find some page underneath that domain that has a problem. Yeah, maybe it's an open redirector, maybe they can inject content. Yeah, so in the case of Facebook, what happened is that what the guy did was he created, handcrafted an authorize request and pointed to his own Facebook page as a redirect URI and sent it to friends, right? So they clicked the link, they went to Facebook, they got single sign-on, the token got, the code got created and got sent to this guy's Facebook page. So far, nothing dangerous, right? I mean, people were seeing the Facebook page, they were thinking like, what's going on here? But that was a bit cleverer than that, yeah? So what he did was, on the Facebook page itself, he posted an image that came from a server that he controlled, yeah, from his own server. And basically now what happens is, imagine the browser goes to the Facebook page. In the URL, there's the authorization code coming from the authorization server. The browser sees that image, it makes the outgoing network call, and on the referrer header, the browser puts the current URL, which includes the code, okay? And that means now that the code got leaked to a server that was under control of the attacker. So the attacker only had to look at his log files in the web server log files and harvest those codes, and now turn these codes into tokens. Brilliant. I mean, I highly respect the guy that found out how that works, yeah? Now you might think, but what's the problem with leaking a code, right? I mean, didn't we just say to turn a code back into a token, you need a client secret? Absolutely right. For confidential clients in OAuth, a client secret is required to turn a code into a token. But is that really stopping attackers? There's another attack which is, became more popular. It's called authorization code injection. And the idea is, yes, absolutely, to turn a code into a token, you need to know the client secret. But what if you can trick the original client application into turning a stolen code back into a token using its own secret? Yeah, is that good enough? Yes, and it turns out it is good enough. So imagine an attacker is able to steal an authorization code using any of the techniques we just talked about, right? Leakage, redirect URI tricks, whatever, yeah? So now he has a stolen code. So now what the attacker can do is handcraft the callback URL, open the application himself, the legitimate application, handcraft the URL, insert the stolen code, and then send it to the client. And what will the client do? He will happily take that stolen code with the client ID and the secret and turn it into access tokens. These access tokens are not available to the attacker directly, but the attacker is now logged in as the victim into the application and can do whatever the application can do. And I guess that's, in most cases, that's good enough. Okay, so yeah, authorization code injection is definitely possible even with Code Flow. So how do we fix that? Well, there's another thing called proof key for code exchange, PKG, yeah, as many people call it. And the idea is with PKG that you are introducing a per request secret that the attacker cannot know, and basically proves that the client is the same client on the front channel and on the back channel. So the way this works is basically is that the client creates a secret, a random number, and hashes that random number, which is called the code challenge. And then he sends the hashed version of that over the authorized request. And then the authorization will store that hashed version. And then when the code comes back on the back channel, the client will send the clear text version of that secret. And now the authorization server has both the hashed version and the clear text version. He can hash the clear text version, and if they match, the client has proven that he is the same client on the front channel as it is on the back channel. Okay. Now in our injection scenario, if the attacker does not know the original, so the client that the attacker uses to hand in the stolen code is not the same client instance that was used in the first place to leak the code. So the code verifier doesn't match. So the authorization server will reject the request, and that is how you solve injection attacks. Okay. A similar attack, which is just the other way around, I guess, is basically by using leveraging cross-site request forgery, where the attacker pre-creates a legitimate code, right, and then basically creates a callback URL, sends that to victims, and tries to force them into the same logon session by them handing in a code that does belong to a different logon session. And that is very similar to a session fixation attack back in the days when we had, session IDs on query strings, right? Again, same thing can be fixed with PKG. If you cannot enforce that PKG is being used, the client can, on its own, implement countermeasures by using the state parameter in OAuth, where basically the idea is that the client creates a secret, stores it locally, puts it on the state parameter, and then the authorization server must echo back that state parameter, and then the client can check that the secret that he put in here is the same and correlates to the request. And since again the attacker cannot know that secret up front, clients can detect that whatever callback they just got sent does not correlate to any request they made in the first place. So the recommendation is to do both. Implement PKG as well as do the anti-CSERF technique, with the state parameter, so that you have a little bit of defense in that field. Okay, so that's basically that. That's the overview. Always do exact matching of redirect URIs. Make sure your callback pages are locked down as possible. Always use PKG. Use the state parameter. And for example, a very easy way to fix the referrer problem is by using referrer policies, or use the no referrer, attribute, for example, so that the browsers don't generate them. Okay, let's move on to something more esoteric, maybe. Yeah, that's what we call a mix-up attack, and a mix-up attack has a couple of assumptions here. The first assumption is that the client trusts more than one authorization server. And that was maybe back then, right, in 2012, not really a common thing, but today it is very common, right? Log in with Facebook, log in with Google, or maybe you have a federation gateway in your company that trusts multiple external providers. So that's that, right? So that's the prerequisite. You trust multiple providers, and maybe somehow you have a self-service portal that allows users to register their own providers. Again, think of software as a service scenarios. And one of those external providers is evil, okay? It's an attacker authorization server. So for the purpose of this illustration, we have two authorization servers. One is the honest AS and one is the attacker AS. So imagine, the user selects the honest AS to log in. And now this variant of this attack has one assumption, namely that the attacker is able to manipulate the HTTP traffic. Maybe it's a browser extension, maybe it's something in JavaScript, whatever. But basically the point is that the attacker is able to, on the fly, change the selection from the honest AS to the attacker AS. So the client application will think, okay, he selected the attacker AS, let's send him to the attacker AS. Now, on the way back, the attacker again is able to modify the traffic and switches it back to the honest AS, so the browser will actually go to the selected authorization server. Okay, so the user will not see any difference. Now he will authenticate and so on and so forth. The authorization server will send back the authorization code. The code will go back to the client. The client still thinks that the attacker AS was selected, so he will happily send his code and his secret and so on to the wrong authorization server. So all the AS now needs to do is basically take that client ID, secret, and code, and he will be able to get the access tokens. Okay, so that is what we call a mix-up attack, basically because the client mixes up the two authorization servers. Now, this has the assumption that the attacker can modify network traffic. And you might be saying, well, if that's the case, I have bigger problems. Yeah, yes. But let me show you another version of that where this is not necessary. Okay, so that's another variation of that. And this time, the user selected the attacker AS to start with. So, you know, maybe he clicked the wrong button. Maybe the attacker AS has a logo which looks very similar to the thing that he really wants to select, whatever, right? He chose the wrong authorization server. Okay, so far so good. Now the client sends the user to the attacker AS. Right, the attacker AS knows, well, he doesn't expect to come to my place, so he immediately forwards the browser to the honest AS by rewriting the client ID and the redirect URI. So now the user will see the real authorization server with the real login page and so on and so forth. He will log in, then the honest AS thinks that is a legitimate request coming from the client and will send the code back to the client, right? But now the client gets the code from that attacker AS from the honest AS, thinks the attacker AS has been used, and again sends the code and the secret to the wrong place, and now the attacker can turn it into tokens. Okay, so that's an example of when I said like mounting additional endpoints gives us very interesting attack scenarios. So if you're not prepared for that, this is a pretty interesting attack. Now, the good news is, if you're using ASP.NET Core, then you are secure by default, and the way they prevent the mix-up attack is by giving each external provider a unique name and a unique callback URL. Okay, and what they do basically when they generate the authorized request, you see that they come up with a random number, which they call the correlation ID, and they encrypt and sign that with the data protection API in ASP.NET Core, and then drop a cookie, which has the format of correlation.authorization server name .correlation ID, which is the random number they just created. Okay. Now, when the response comes back on the authorization server specific callback URL, the protocol says that whatever is on the state parameter must be sent back. So this contains our encrypted and signed correlation ID. So what they do is basically they validate the signature, decrypt the value, and now have the clear text correlation ID back. And now they make sure that there is a cookie called correlation.authorization server name .correlation ID. And if that cookie doesn't exist, somehow there's a mismatch between the thing that started the flow and the thing that finished the flow, and they will reject that. And maybe you've seen that before. There's an exception called correlation failed that can happen for other reasons as well. But that's how they stop basically these mix-up attacks. Okay. So if you're using ASP.NET Core, you are fine. If you're using any other framework, you should have a look how they implement protection against these types of attacks. Okay, so let's switch gears for a moment and look at public clients. Yeah, like like things like mobile applications or spas. Yeah, public clients have slightly different rules, right? I mean, you cannot authenticate them in essence because it's a public client. They cannot store a secret, so you cannot rely on any client authentication like we can do for confidential clients. Yeah. So let's have a look at the first anti-pattern that the BCPs point out, especially for native client applications, which is native login dialogues, right? So it's a very common thing, and that the native application brings up its own login page where you type in the name and the password, right? And if you are unlucky, you have a really good password and you have to type it in now on your phone. And then they send that to the token service, get back the token, and so on. So this is using the password grant that I mentioned earlier that is now deprecated and shouldn't be used anymore, right? I mean, yes, I know. You wouldn't believe how many hours of my life I wasted with product owners discussing why this is bad. They say like, it's my client, it's my user, it's my backend. What are you telling me? Yes, I cannot, I cannot force you to do the right thing, but we know that this is not the best way of doing it. You should rather let the user type in the password in the place where the account is stored, which is on our authorization server, which means you have to open a browser to show the login UI, which I think is the better way of doing it, but that's just me. That gives you support for password managers and for all of your logging and auditing and your advanced authentication methods and federation and all these things, right? And because you are using the system browser here, you potentially get single sign-on as well with your whatever you are logged on to already in on your machine or on your phone, right? So that's the recommended way of doing it. So use the system browser. Every operating system has a way of doing that, right? The mobile ones are a bit more advanced here because they give you a better UI or UX rather, to show the browser, put the browser away again. On desktops, you've probably seen that before. It's sometimes a bit weird that the browser opens up and suddenly it's in the front of the application and so on. Still, these things can be fixed. And then you have to figure out how to do the callback from the browser back to the application. There are a couple of ways of doing that. Again, I would recommend reading that document because it has all the details. But the best way of doing it is what they call claimed or universal URLs, and you've probably seen that before, right? When you open a link on your phone to Google Maps, and instead of the browser, the app is opening on the phone. So there must be some way of knowing that this URL belongs to that specific app. And the way this works is basically that you're dropping on that URL a special document, which is signed, which tells basically the operating system that, hey, if this app is installed on the phone, rather forward that link to that app, otherwise show it in the browser. That's how you can implement the redirect URIs for native apps, which is a very elegant way of doing it. Okay. Token storage is always a concern, and we talk about that in a second in the context of browser-based applications. For native ones, you have the luxury of, well, not storing them in the browser, I guess. You also have access to native operating system APIs, like, the keychain on iOS or DP API on Windows, and you can put additional things on top of that, like Face ID or Touch ID or things like that. Also, it's a good idea to clean up when you're done, like revoke refresh tokens at logout time or when the application uninstalls and so on. And again, you'll find more of that good information in that native apps BCP. The last BCP I want to talk about is the browser-based ones, which is, a sad one, I guess, because we just can't fix those browsers. It's a lost cause, right? But ultimately, right, the main problem with browsers is that they are shared execution environments. They are just like, these days a little bit like operating systems, yeah, with every tab running in different processes and so on. But one thing that is still shared typically are cookies, yeah, between, because that's how the web works, I guess. But the interesting observation is that many attacks start with the word cross, right? Because it's somehow one side attacks another side. And that is due to the nature of this shared execution environment. Now, this is a topic for a whole day, I guess, but you all know that there are basically two fundamental ways to write sparse these days. One is you're relying on browser built-in features like cookies, or the other one is that you're driving it from the application like access tokens. The cookie approach historically has cross-site request forgery problems. The token approach has historically cross-site scripting problems, yeah? So it's a bit of a, choose your poison, I guess, yeah? If you look at these BCPs, they give you two fundamental ways how you can think of JavaScript-based architectures. And this might sound backwards, because for many years now, this was the style that was advocated by JavaScript people, the JavaScript application without a backend, right? Basically, this dream of you can just download your JS file and your HTML from a CDN, no backend needed. We do everything in the application. Yeah, very hard to secure. Yeah. In this scenario, the client has to do everything. Request the tokens, manage the tokens, store the tokens, and that's the hard part, and do the lifetime management and so on. The more, coming back, more and more people are using this type of architecture, which I personally recommend as well, which is basically that you have, in addition to your SPA, a backend that belongs to the SPA that stores the tokens, manages the tokens, calls the APIs on behalf of the SPA, which means no tokens stored in the browser, which means, you know, cross-site scripting cannot exfiltrate them. And, you know, I mean, there are many arguments going, you know, back and forth, but I think this is the easier threat model. That's my personal opinion, which basically brings you to such an architecture here, right? Which some people call backend for front end or BFF, where you have the front end, which is written in whatever JavaScript framework you like. You have a back end for that, which has the local APIs, which are application specific. You can use an external identity provider. You can call external APIs, but the point is that the front end always talks to them via the back end, and they live on the same site, right? And then you secure that front end back end connection with either anti-forgery, or if you can, with the new same site cookies, yeah, which is a newer feature in browsers. And if all the browsers that you need to support them as well, then you don't have to write any line of code to secure them, because the browser automatically takes care of making sure that these cookies don't leak across site boundaries. Yeah, and you probably remember there was some drama around that in Chrome 80, yeah, introduced, basically made every cookie same site by default, which broke many websites, right? And then they realized, oh, we broke the web, and oh, it was during a pandemic, so they undid those changes again. Now they are back in Chrome 83. So yeah, that's the future. Every cookie on the web will be same site by default, unless you opt out explicitly from that. And you know, that's just the way it is. If you don't like that cookie business and you have to store that stuff in the browser, well, then be aware of that there is no secure data storage in the browser, right? Everything is available from JavaScript, which means if you have a cross-site scripting attack, the tokens are available to the attacker. You can harden your applications, right? Using, for example, content security policy, and, you know, just basically scrutinizing all of the additional libraries you're pulling in from NPM. But yeah, there's that, right? For the session management, you have to make up your mind. How do I want to do the token management? There are two options here. One is using session bound techniques, which are getting harder and harder these days because of things like intelligent tracking prevention in Safari, and, you know, Brave has the same thing now, and more browsers are coming. Or you do refresh tokens. Yeah, refresh tokens are even more dangerous in the browser because they are typically longer lived, and there are some techniques that you can apply to them. For example, rotating the refresh token, detecting replay attacks, and so on. But these are things that you have to implement on top. Okay, and again, I can only recommend, if you are writing SPAs, read these documents. They are useful to read. Okay, which brings us to our last topic, OAuth 2.1. So for the last 57 minutes, I talked a lot about documents that add rules to OAuth 2.0. Okay, so in other words, if you today want to learn about OAuth, you have to read the base specification, then you have to start reading all the BCPs and the threat model, and then you merge all of these documents in your head. And that's basically what you need to know, right? So the idea of OAuth 2.1 is basically to start with a new baseline. And the whole idea is this. We are taking the base specifications, which is RFC6749 and 6750, merge them together. Then we take all the various BCPs I just mentioned and merge them together, and that becomes OAuth 2.1, which is the new baseline for OAuth. And if you want to diff them in your head, basically, the most important changes are this. Implicit grant is gone, password grant is gone, PKG is mandatory for the authorization code grant, redirect URIs must be compared with an exact string match, no regular expressions allowed, things like that. Refresh tokens must either be sender constrained, meaning they are used by confidential clients and the sender constraint is done by client secrets, or they must be one-time use only, which is primarily targeting public clients like spas, where, you know, basically every refresh token usage should result in a new refresh token, and that you can detect it if somebody starts using the same refresh token twice, which probably is then an attack. Yeah. All the bearer tokens must not be sent anymore using the query string for the reasons I mentioned. They leak too easily, you know, log files, proxies, and so on. Okay, so that's basically, that is coming soon. It's not done yet. 2.1. It's I think it will come this year, but these will be the big changes. Okay, so to summarize that, you know, some of the threats we talked about cannot be mitigated, like, you know, network compromise. Some of the threats are easy to mitigate by just, you know, following the rules, like, you know, do anti-CSRF protection, close those redirectors, you know, and so on. And some threats will always be hard to mitigate, even if you have a perfect implementation. And I'm mostly talking about things like, you know, like the MixUp stuff. And if an attacker specifically targets your system and they find the things that you might not have thought about, well, even with a perfect protocol implementation, there is some room here, right? As a summary, I can say, you know, sometimes I talk to customers and they say, like, you know what, after you told me all these things, we don't want to use OAuth. It sounds very complicated and insecure. And all I can say is every security protocol is complicated, right? And because it must be. You cannot solve a hard problem in a simple way. I mean, you can simplify things, but it never will be simple. The beauty about OAuth is that it's public, it's open source, and it's publicly tested and attacked and iterated on. And by using a standard, you get basically a protocol that many people have worked on, that many people have tried to break. And if you come up with your own protocol, then maybe you are the only person that worked on it, and you are the only person that tried to break it, and maybe you didn't succeed, and you think, wow, that must be good. So all in all, you know, yes, OAuth is complicated-ish, but I think it's still the best thing we have today. Cool, thank you. If you have any questions, you can speak up now or leave a question in the Slack channel. I'll try to get to that. Otherwise, I guess it's lunchtime. Thank you. Bye-bye.